Okay, so this is the first video for the take-home quiz, and this will be scenario one or question one. A certain company makes three grades, A, B, and C, of a particular electrical component. Historically, grade A components have a 2% defective rate, grade B have a 5% defective rate, and grade C have a 10% defective rate. So grade A, go ahead and note this, A equals 2%, B is 5%, and grade C has a 10%. So basically, we have better grades. One is better than the other. A is going to have the least amount of percentage of defects. Then it accelerates up to more defects depending on as we move down the grade and become a lower grade. Since grade A components are less likely to be defective, the company can charge more money for those components than it can charge grade B or C components. Similarly, the company can charge more money for grade B components than it can charge grade C components. Recently, the company found a batch of components in a warehouse that were known to be of the same grade, but the grades were not labeled on the components. To determine grade A, B, or C, the company selects from that batch a random sample of 200 components, which contained 16 defective components. So basically, they found an unlabeled box. It had 200, and they took a random sample of 200, and 16 out of the 200 were defective. So part A says, construct and interpret a 95% confidence interval for the proportion of defective components in the batch. Well, according to our recipe, the very first thing we have to do is define the parameter. And the parameter here is the proportion, and then we're going to actually make a 95% confidence interval. So this will be our confidence level right here. So P naught is the true proportion of defects in the batch of electrical components. All right, so P0 is the true population proportion of defects. And please notice, this is the same sentence we've been using, but since we're working with proportions, it's not population mean, we're now looking for population proportion. Okay, continuing on. Our next step on the recipe are the conditions. And the first condition said we took a random sample, and they told us that right here at the very bottom. They said they had a random sample of 200 components. The next thing, we need to check for the N is less than 10% condition. So N needs to be less than 10% of the population, and we had 200 components divided by 0.1 equals 2,000. And it's reasonable to assume that there are at least 2,000 electrical components in the batch. Otherwise, they wouldn't be have such a large sample of 200. They check a smaller sample. So N is less than 10% of the population. We're good. The reason we do that is we're looking to check for overall independence, whether or not there is a significant impact or not by the fact that we're not doing replacement. So one of the key things is a change in percentage negligible? The next condition is normality. And in this case, they actually gave us how many they tested. So in this case, NP is equal to 16, which is greater than 10, because 16 happened to be our number of defectives. All right, this was the number of defectives. Out of the batch of 200. Well, if 16 was the number of defectives, 184 is the number that were not defective. And the way I got that is we had 200 that we sampled, 16 were defective, so 184 were not defective. Because both sets are greater than 10, we have 16 and we have 184. Because they're both greater than 10, the sample is large enough to use the normal approximation. And we're really using the normal approximation for the binomial, which is kind of interesting because the binomial is a discrete probability. It's numbers 1, 2, 3, 4, 5, 6. So the binomial is discrete. Actually, I think I misspelled that. Oh, well, the binomial is discrete and the normal happens to be continuous. So we have an x of 16, which is really important that we have a whole number here. X and n must always be whole numbers when we plug them into the calculator. If they're not, you're going to round. What we don't have is p hat. Well, p hat equals x over n, and we're going to need this because of the way of what our formula looks like. All right, so p hat equals x over n, so 16 over 200. So p hat equals 0.08. So we have p hat equals 0.08. And if that means q hat, which is 1 minus p, so that means q hat is going to equal 1 minus 0.08, which equals 0.92. All right. If we write our formula down, we're going to end up with a formula of p hat plus or minus z star p hat q hat over n. And by the way, whenever we're working with proportions, if we're working with proportions, we're working with a z. All right. So we now know that p hat is 0.08, so we can go ahead and plug in p hat for we can plug in the 0.08. So 0.08. We'll come back and I'll remind you how to do z star. And we have 0.08 over times 0.92 over our entire sample size, which in this case happens to be 200. All right. So let's go back and calculate z star. And z star is going to be under the second vars function of the calculator. So let's go there. Second vars, inverse norm. And they wanted to calculate a 95% confidence interval. So we're going to go parenthesis 1 minus 0.95 close parenthesis divided by 2. We have a mean of 0, and then we have a standard deviation of 1. And the reason we're using a mean of 0 and a standard deviation of 1 is because we're calculating a z. That is, all z's have the same mean if we remember the empirical rule. Mean of 0, standard deviation of 1. Or I should say the standard normal. And we get a z star of about 1.96. Now, I recognize we probably should carry it out more decimal places. But for ease, that's what I'm going to write. Well, after we have that down, we've now plugged everything into our formula, so things look nice and good. All right. So then I need to calculate the actual interval. To go to the calculate the interval, I'm going to go to stat, arrow over to the word test, and I'm going to drop down past z interval because I'm looking for one proportion z interval. And there it is at letter A. So one proportion z interval. And the very first thing it asked me for is my x. Well, my x in this case is my number of defects, which is 16. My sample size was 200. And then we need to plug in our confidence level, which is 0.95. And so I end up getting a lower bound of 0.0424 and an upper bound of 0.1176. So that's my interval. So then I need to write my conclusion. And in my conclusion, we are 95% confident that the true population proportion of electrical defects, there's electrical defects in the batch, but we can shorten it up, proportion of electrical defects lies within the interval 0.0424 to 0.1176. Now, what I did not include was that in repeated sampling, we expect to capture the true population proportion of electrical defects 95% of the time. And the reason I didn't do that is it wasn't required. Okay, if they'd asked for me to interpret the confidence level, if I have to do the interpret the confidence level, the key phrase being confidence level, then I must do that. And my confidence level is 95%. And if they asked for me to interpret the confidence level, I would have to say the unrepeated part. They did not, so I didn't do it. This is the conclusion right here. And you always, 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 always have to include the conclusion. All right. Then there was a part B. All right. And part B asked, based on the interval, does the interval calculated in part A, and our interval was 0.0424 to 0.1176, does the interval calculated in part A allow the company to clearly determine the grade of component that was produced in the batch? Well, we should look up, and earlier we said, okay, we had 2%, we had 5%, and we had 10%. All right, so that grade A had 2% defects, grade B had 5% defects, and grade C had 10% defects. So I should look at my interval. And one thing I clearly see when I look at the interval is what could be included in that interval. Well, 0.02 is below it. So grade A, it's not grade A material. But when I look at it, it could be 0.5 and 0.10 lie in the interval, so it could be grade B or grade C. So we know it's not grade A because it's not in the interval, but grade B and grade C lie within interval, so it could be either one of those. And so that's what we're going to say. Because 2% does not lie within the interval, the batch cannot be grade A. So in other words, it cannot be the expensive components. However, both 5% and 10% lie within the interval. Thus, we cannot determine whether or not the batch is grade B or grade C components. So it could be that we're dealing with either grade B or grade C, but we know it's not grade A, so we can't charge the more expensive price. And because it includes grade C and we don't know, we're gonna probably have to charge the cheaper price. Okay, they didn't ask that, but the interpretation would be can't charge the grade A price because we know it's not grade A, and we probably need to charge the grade C price because we're not sure if it's grade C or not. So for ethical reasons, we're probably gonna have to charge the grade C price because it lies within the interval.